Hello and welcome to a new video. In this video we're going to talk about SRAMs and the material is spread over two videos, so we'll cover the SRAM over this video and the subsequent video. So memory has been playing an important role in the design of processors, SoCs and GPUs. The on-chip memory has been increasing in size over the last decade, primarily driven by the need for fast data processing. And therefore, because a large part of the chip is the memory, the power and the speed of the memory dominate the performance of the system, and hence you need to choose the memory and the interfacing carefully for your application. So what we'll do now is we'll talk about the types of memory that are available and then look at the terminal characteristics of an SRAM. So let's think about array subsystems in general. So if you think about memory arrays, they can be broadly classified into three broad categories. The first one is the random access memory, and this is a memory where you can access data at any time. So you give an address and you get a bit out. Something known as serial access memory. In serial access memory, the data is always in a serial fashion. And the last one is a content addressable memory, where you can give a piece of the content that can return back all the cells in the memory that have that piece of content from it. Right? So you can access the memory either using random access, a serial access, or content addressable memory. Now, if you think about serial access memories, the common examples are shift registers and queues. Right? And shift registers again can be thought of in two design styles. One is a serial in parallel out shift register, or the opposite, which is a parallel in and a serial out register. Similarly, queues can be roughly broken into two types. One is a FIFO queue, or a first in first out queue, or a LIFO queue, which is a last in first out queue. If you think about the random access memory can be again thought of into two broad categories. One is known as a volatile memory and the other one is known as a non-volatile memory. So volatile memory is the memory whose stored values are lost when you remove the power supply to the chip. A non-volatile memory, on the other hand, retains the values in the memory even after the power supply is cut off. So in the volatile memory, we have two broad categories. One is known as the static SRAM, on which we're going to focus for this and the next video. And we have the dynamic RAM, or the DRAM. Non-volatile or ROM, read-only memory, again has multiple subdivisions, and this is mostly historical. So started off with masked ROMs, which then moved on to programmable ROMs, and then erasable programmable ROMs, EEPROMs, or electrically erasable programmable ROMs, and today where we are, which is the flash device. The flash device is based off the EEPROM, but the device has substantially moved on from what it was initially. Now, let's look at a typical memory array. So a typical memory array, the data is stored in bits, and there is a basic building block of the memory in which the data is stored, and that is known as a bit cell. Now a digital memory or system usually operates with words, which are nothing but a set of bits. And any memory array, if you think of, typically would contain 2 to the power n words made up of 2 to the power m bits. Right? And so each of them would be stored, each bit, so a 1 or 0 would be stored in a bit cell. And sometimes to improve the aspect ratio, we sometimes fold memories. So if you think about how a memory cell is organized, you have a few memory cells. So your memory cells are sitting here. Now you need to access the various bit cells. So the various bit cells are accessed using what is known as a row decoder. And the row decoder is able to access or enable a particular bit cell in this entire array. And then we sometimes have another column decoder, especially if you have dense memories, and so with the with the help of the row decoder and the column decoder, you can single out a single bit cell from which either data can be read out or data can be stored in it. So in a SRAM and DRAM, data is going to be written or read bitwise from the memory. Now, why is an SRAM typically used? So SRAM is one of the most common memories we use for on-chip memories. And so how does it differ from a flip-flop, which we have seen earlier? So first thing is, an SRAM is much denser. It's a very small cell, so it's denser, so that we can pack more memory on the chip. It is compatible with standard CMOS processing, which is always an advantage. It is faster than the DRAM, so this supports high bandwidth memory, and therefore, especially for large data compute operations, the SRAM is preferred over the DRAM. And finally, it's also easier to use than the DRAM. It doesn't require refreshers, etc. So in general, the SRAM is a much better memory than the DRAM when it comes to speed of the memory and the usability of the memory. And so therefore, it finds use in applications such as cache, register files, tables, scratchpads, etc. So any compute system you think of typically has a lot of on-chip memory, which is mostly the SRAM. So now if I think about an SRAM, most of the time what we're going to focus on here would be a synchronous SRAM. And what I mean by a synchronous SRAM is that it has a clock signal which is going to govern its read and write operation. So to refresh your memory, if I think about the SRAM now, the SRAM has a memory array, right? It has two types of data inputs. A data input, which is what is needed when you want to write data into the memory, and addresses. Now these addresses are the locations of the bit cells in the memory, right? So by supplying an address bit word here, you can tell the memory which particular bit cell do you want to read from or write into. We have a data output pin, and the data output pin is basically going to give out the bit cell data when you perform a read operation. And to synchronize all these operations, we have a bunch of control signals. And so you have to, whenever you want to operate the SRAM, in addition to these addresses and data signals, you need to make sure you have the right control signals enabled so that data read or data write can be accomplished. Now, a couple of things about the SRAM timing diagrams. A few important times, if you will, that you would use in an SRAM or you would look in an SRAM data sheet. The first one is known as the access time, and the access time is the minimum time required to read a bit of data from the memory, and it's normally measured from the rising edge of the clock in the read operation. And when you measure these times, they're normally measured for a specific load, for a specific temperature and VDD, right? And so if your operating conditions are different, make sure that you characterize the SRAM for that particular process condition. The next time is the cycle time, or the amount of time that is required to perform a single read or a write operation. And most importantly, to reset the internal circuitry so that the memory is available or ready for the next operation to come in. So this determines the speed, if you will, of the memory. Now I'll use an IBM SRAM to illustrate the operation of the SRAM memory. So you do need quite a few control signals to ensure that the read and write operations are done successfully. So all operations typically are controlled by one clock signal, right? And each of this control signal must be appropriately set and be valid when the clock edge comes. So the first signals are obviously the address signals, normally denoted as ADDR, and that's used to select the memory location in the chip. Beyond that, we have data inputs and outputs. So we have data pins on which we place data when we want to write into the memory cell, and DOs denote the data output pins where the data becomes available once the read operation is completed. Normally, good designs, what they would do is when not in use, that is when there is no read or write being performed on the memory, you'd see that these data output pins are typically in high impedance state, and that allows you to multiplex different memories together. We have what is known as an output enable signal, And this signal is to tell the user when the outputs are active. So when the signal is low, it indicates that the outputs are active. And during the write operation, this signal is particularly ignored, right? So we use this signal to indicate when the read operation is completed so that the user can then use the data available at the output pin. And this is not a clock signal, but rather is an asynchronous signal. We also have the primary clock, which is sometimes denoted as K. And this is the clock across which all the input signals are latched to. We also have a chip enable or chip select signal, and this is to ensure that you enable the chip or to block signals in case the chip is not enabled, right? And so CS has to be low, or CS bar has to be low for the inputs to be applied to the chip. We also have another signal which is known as the write enable signal, and this is used to choose whether we want to do a read operation or a write operation. And so write enable will tell the memory whether it is a read or a write operation. So now let's look at a typical read operation on a SRAM memory. So these are all the signals that would be used in a read operation. So you first have the clock signal, then the address signals, then a chip select signal, a write enable signal, an output enable signal, and the data out signals, right? Now before the clock goes high, so clock going high indicates that the read operation begins. So before the clock goes high, we need to ensure that the address has settled down on the address pins. So which means that before this edge, address should meet the setup and hold times. Additionally, the chip select signal should be enabled to ensure that the chip is ready for the read operation. We send the write enable signal high to tell the memory this is a read operation. Again, this signal has to be sufficiently settled before the clock edge comes in, so it has a setup time and a hold time. And then you also have the output enable signal, which goes low once the read operation begins. And so once the read is completed, data shows up at the output pin, and so whatever is stored at address A0 shows up as on the output pins as DQ0. Similarly, once this cycle is completed, during the next cycle, I give an address A1 and then I pull the data out at DQ1. So you see that within one cycle, data shows up from the address onto the output pins. Right? So for a read, the output enable signal must go low, and if it is not activated, then the output is essentially in a tri-state. So to ensure that the data is ready and available post the read, this output enable has to go low. And the data appears at the pins after an access time. So the access time denotes what is the fastest time when data is available when an address is supplied at the SRAM. Now there are different types of reads that are available. So in the IBM SRAM, there are three types of read operations that are available. The first and the simplest one is the flow-through mode of read, in which both the address and the control signals are set up before the rising edge of the clock, and the data appears within the same clock cycle after an access time. The second kind of read is known as a pipeline read, in which case the control signals again are set up prior to the clock edge. However, the data that is read is stored in an output register and then transferred to the output pins in the next cycle. So there is a delay between when the SRAM reads the data to when it is available at the data pins. The third kind of read available is known as a register to latch. And here again, the addresses and the control signals are loaded into an input register at the first clock cycle. And the data that is read is stored in latches and is transferred to the output pin when the clock goes low. So this enables the user of the SRAM to have freedom to choose the timing of when the data will be available at the output pin. And finally, you have what is known as a burst mode read, in which several bits of data can be accessed from one address. And how that works is you have an on-chip counter which updates the address, and continuously data is streamed out synchronous with the clock at the output pin. Now if you look at the write cycle, The write cycle again has these signals: the clock signal, address, chip select, write enable, and the data input pin. So before the clock goes high again, the address needs to be applied. This is the address where you want to write the data into. Chip select has to be selected. Your write enable has to be sent to 0 to indicate that you're doing a write operation. So again, this write enable has to meet the setup and the hold times of the signal, and the input at the data input pin should be available before the clock goes high. And once the data is applied to the pins and it satisfies the hold and setup at that point, then data gets written into the memory. So when the clock goes high, the write operation begins and data is stored in the cell. With this, what we'll do is, with the basic understanding of how the SRAM works, we will now in the next video look into how an SRAM is designed, the transistor level schematic of the SRAM, and then we'll look at how the read and write operations are managed at a bit cell level.